For nearly a century now, one of the most famous arguments in history of science remained nothing more than just a thought experiment. Mostly because it was based on such complex ideas that it was practically impossible to prove using experimental evidence. And here I'm referring to the famous debate between Albert Einstein and Niels Bohr, whose picture you see right here. And so their ideas were so ridiculously complex and involved such tiny scales that they could only debate and discuss these ideas using pen, paper, and their imagination. But it just so happens that in 2025, a team from China actually managed to finally create the necessary experiment to prove one of these ideas, and managed to build one of these legendary experiments in the lab. And well, I'm sorry, Albert Einstein, but turns out that you might have been wrong. And so, hello wonderful person, this is Anton. Today we're going to discuss the study you see behind me on the tunable Einstein-Bohr recoiling slit Gedanken experiment in the quantum limit. Yep, lots of super complicated words. But the main point of this video is to explain exactly what this experiment was and what it was able to prove. So here we're going to discuss how a single atom managed to settle this 100-year-old debate, with the results actually telling us something fundamental about the universe itself. But I guess let's first discuss exactly what Einstein and Bohr were arguing about, and what exactly their main disagreement was. And here it all starts in 1927. This was the 5th Solvay Conference, and technically this was a gathering of some of the world's greatest minds, mostly to discuss and to debate a lot of different propositions. And the most famous such debate was, of course, here. Albert Einstein versus Niels Bohr. And the thing is, back then Einstein was super uncomfortable with the newly proposed laws of quantum mechanics. He actually famously stated that God does not play dice with the universe. In other words, he did not believe that quantum mechanics fundamentally was showing us the true universe. He believed that the world should be more predictable, more logical, and that every particle should have a definitive position and definitive momentum and speed at all times. Bohr, on the other hand, proposed almost the opposite. He championed something referred to as principle of complementarity. In essence, he argued that particles like photons can act both as waves and particles, but you can never measure or you can never observe both properties or both behaviors at the same time. If you measure where a particle is, for example, you lose the information about its wave side completely. And well, Einstein really didn't like that. For him, this was a direct sign that quantum mechanics was just incomplete, and as a theory, it was not yet ready. And so to prove Bohr wrong, he proposed a clever modification to the classical double-slit experiment. Now, in the standard version, you fire photons, usually lasers, at two separate slits. And on the screen behind them, you see a kind of an interference pattern, a series of bright and dark stripes that proves light acting as a wave. But Einstein's gotcha moment in this case was the idea of a movable slit. Basically, he imagined the first slit was hanging on very tiny sensitive springs, which would then be affected by a photon passing through one of the slits, and it would give one of these slits a tiny kick or a momentum recoil. So basically something maybe like this. And so Einstein argued that by measuring how the slit moved, you could technically figure out exactly which way the photon went without destroying the wave pattern on the screen. Or in other words, you suddenly could maybe discover both properties at the same time. And if this worked, the principle of complementarity would crumble right away, or at least it would in theory. And for 100 years, this essentially just remained a Gedanken experiment, or a thought experiment that Einstein was so famous for. But the thing is, Bohr did have a response. It was subtle but brilliant. Here, Niels Bohr argued that for the slit to be sensitive enough to feel the kick, the slit itself must be so light that it also obeys quantum laws. This is because of the famous Heisenberg's uncertainty principle. And so if we know the slit's momentum well enough, and if it feels this kick, its position actually becomes fuzzy as well. And it's this fuzziness that would then blur the interference pattern, meaning that you still could not see both properties at once. In other words, Bohr's explanation made sure that quantum mechanics remained intact. But the problem here was that we could not test this either. And that's because a single photon or a single atom have almost no momentum at all. And so for a regular macroscopic slit, the ones that we usually use in the lab, in for example like a physics class or something, here in order to feel any kick, you would need to be impossibly light and incredibly still. So in other words, trying to conduct this in a lab would be very difficult unless it involved some kind of a different setup. And until now, we simply did not have the technology to make the slit that was basically quantum enough. And that's precisely what was now achieved in this new experiment from China. In this recent study performed by Jiawei Pan and his colleagues from the University of Science and Technology of China, instead of using a piece of metal with a hole in it, they relied on something that's already been used in a lab in quantum mechanical studies many times, the atom of rubidium. And so by using a single rubidium atom, trapped in something referred to as optical tweezers, they were physically able to recreate all of this and prove Bohr correct. And first they had to cool down this atom. In this case, they had to use lasers. By trapping this atom between lasers, they cooled it down to its motional ground state, effectively making it stationary and extremely sensitive. And what's really brilliant about this experiment is that in this case, this atom now becomes the slit. In other words, it starts acting as a movable slit proposed by Einstein. Which means that now they just had to fire some photons and observe what happens. And that's exactly what they did. They fired single photons at this atom and then watched the results. And so here, by changing the depth of the laser trap holding the atom, they could then control the atom's momentum uncertainty. And when the atom was set up in just the right way to detect the photon's kick, the interference patterns on the detector blurred and disappeared, which is exactly what Bohr predicted originally. And so what makes this experiment so interesting is that researchers could dynamically adjust the atom's momentum uncertainty, allowing them to observe a gradual transition from wave-like behavior, or basically clear interference, to particle-like behavior involving blurred fringes. In essence, confirming that the visibility of interference seems to be directly determined by the degree of quantum entanglement. And so as you try to measure the momentum or the kick more precisely, here the entanglement between the two increases, destroying the interference pattern. And that's a direct support for Bohr's principle of complementarity. In short, while Bohr just used logic to show that measuring the slit would necessarily blur the results, the Chinese experiment used a single atom to prove that blurring happens exactly as quantum mechanics predicted, even when the observer is as small as a single atom. And this is of course a major milestone for quantum physics. It moves us beyond just theory and speculation into actual physical evidence and quantum observations. It also confirms that these patterns seem to be determined by quantum entanglement, and the photon and atom in this case become entangled just as the theory predicts. And at the same time, it also demonstrates a kind of a quantum to classical transition. In other words, it directly shows us where the weirdness of quantum world ends and the normal world of classical physics begins. And so here this is not just about winning some kind of a debate, it is about trying to understand exactly what quantum physics seems to represent and how the actual world and the universe itself seems to work. But I guess in the end, Einstein was still wrong and Bohr was still correct. And so it does look like nature by itself has a kind of a built-in privacy setting that prevents us from seeing the full picture of wave and particle behavior at the same time. So definitely a pretty exciting experiment. But in this case, as the researchers in China show us, when you try to cheat the system by watching the slit, the universe blurs the results to basically keep its secrets. And that by itself is a pretty exciting discovery, but also a reminder that even the brilliant minds are sometimes incorrect. But in being incorrect, they actually push the boundaries for our own understanding and help scientists create these incredible experiments that then reveal the universe as it truly is. But at least for now, that's pretty much all we have. There are some other experiments we're going to be discussing really soon because some of them actually show us something else about the universe. But until then, thank you for watching, subscribe, come back tomorrow to learn something else, support the show on Patreon where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access and a few more things. And that way, I don't have to get any more sponsors. You can also buy the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye-bye.